So what are we trying to figure out in this one? We've got this pipe, point A higher up, point B lower down, a pump in between. What's our goal in this one?
Oh, sorry. Calculate the resistance?
Yeah, we're trying to find the resistance of this section of pipe. And we're given information in kind of an unusual way here. It tells us what happens with the pump and also what happens without the pump. And I think it's probably best to treat that as if this is two different fluid systems, a pipe with the pump and a pipe without the pump. So if we think, because you can't really use a Bernoulli equation to compare two different situations with two different times. So instead what we want to do is set up both situations and check the Bernoulli equation for each one.
That's like the whole question about like comments, right? What you're talking about, like,
would you be willing to mute that? There's a lot of background noise going on. Thanks. So if we set up both systems, a system with the pump and a system without the pump, let's see what that's going to look like. I'm just going to draw this side by side. If we've got effectively the same setup, but with no pump. And I think we're assuming uniform cross-sectional area here. Yeah, because it doesn't say anything about cross-sectional area, and it looks like it's probably the same throughout. So comparing these two different systems. If we were to write out a Bernoulli equation comparing points A and B without the pump, what would that Bernoulli equation look like? Yeah. And let me just paste in the complete Bernoulli equation for each one of these, and then we can delete terms that aren't needed. So without the pump, there could certainly be a pressure difference. In fact, if we write out, do you want to write this as A minus B or B minus A?
B minus A.
Okay, let's say B minus A. And we could go either way. The important thing is to just be consistent about it. So let's say in both cases, we're going B minus A. So delta pressure would be pressure B minus pressure A. And then rho G delta Y, density of the fluid times gravity times, and then for delta Y, B minus A, would that be positive H or negative H? Yeah, it should be negative because B is a lower height than A. So height of B minus height of A will be a negative value. We could even treat height B as 0 and height A as positive H. So final minus initial would be 0 minus H. So delta Y will be negative H. And do we know anything about speed at point A and speed at point B? Yeah, points A and B, I think we can assume they're the same cross-sectional area, so that suggests no difference in speed. So we can ignore the speed term entirely. And in the without a pump situation, we certainly would not have the pump term. Is there current and resistance here? Cross-sectional area would be the area of the cross-section of the pipe. Like if you imagine this pipe, if you slice it across the cross-section and then measure the area enclosed within, that's cross-sectional area. And the important thing is that in any section of pipe, the current should be uniform throughout that section of pipe. So the only way the speed can change is there's a difference in cross-sectional area. Yeah, we definitely have current flowing. And presumably this pipe does have resistance, since what we're trying to find is the resistance of the pipe. So that means we should include the negative IR term. Also, do we know which direction water is flowing?
Downhill, so left to right.
Yeah. So let's mark that on the diagram. Just with some arrows. Just to show a direction of current. And subtracting B minus A, if you think of that as final minus initial, if you think of A as initial and B as final, that is the direction current is flowing. A is flowing, or current is flowing from A towards B. So that means that we can treat current as positive. If current were flowing the other direction, but we were still looking at it as from A to B, then we would treat current as negative. So in general, current can be positive or negative depending on which direction it's flowing versus which direction we're treating as final to initial, or initial to final. Any questions on that setup so far? Positive or negative for current is all about direction. If we're subtracting value at B minus value at A for the deltas, we're effectively treating B as final and A as initial. Not in terms of time, because we're assuming no time is passing here. This is all one instant in time. But subtracting B minus A is treating A as the initial location and B as the final location. Current is flowing in that direction from the location we're treating as initial towards the location we're treating as final. So we will treat current as a positive value. If current were flowing the other direction, we'd have to treat current as a negative value. Or alternatively, if we had been subtracting A minus B, that means we'd be treating B as initial and A as final. The current's actually flowing from A to B. So if we were treating B as initial and A as final, we would have to treat current as a negative value. We would still write this term as negative I times R. It's just that the value of current would happen to be a negative number. Any other questions on that so far? And by the way, the same thing is going to apply when we're dealing with electrical current. With electrical current, you choose a direction in the wire to call positive in the sense of from initial to final. If current really is flowing that way, then current will be treated as a positive value. If current's really flowing the other direction, then current will have a negative number as the value. You'd still write out the equation exactly the same way, but the value of current could be positive or negative depending on which direction it's flowing. Meanwhile, for the with pump situation, I think we can write out exactly the same left side, because the left side still has a change in pressure and a change in height, same change in pressure, same change in height as before, and no difference in cross-sectional area. So the speed at A and the speed at B will be the same as each other. But now there is a pump, so we'll include the E pump term. Any questions on that so far? And it looks like in both of these cases, if we compare these two equations, we can essentially treat this as a system of two equations with some unknowns. But there's a very useful way we can combine these. We know that on the left side of the equation here, we've got information about the pressures and the heights. On the left side of the equation here, we also have the same information about the pressures and the heights. So what can we do with these equations? Yeah, we can set the other sides equal to each other. Since we know PB minus PA plus rho G times negative H on this equation is exactly the same as PB minus PA plus rho G negative H on this equation. That means the other parts, the negative IR here, can be set equal to the E pump minus IR here. But keep in mind that the currents are different. What do we know about the currents? Yeah, there's no difference in speed because remember, we're comparing the speed at A and the speed at B. What's the only way those speeds could be different? If there's different area, yeah. If the pipe at location A and the pipe at location B have different cross-sectional areas. If they have the same cross-sectional area and they're in the same section of pipe, they've got to be going at the same speed as each other. And note that we're not comparing the speed at A and B with the pump to the speed at A and B without the pump. We're just comparing the speed at A and the speed at B. So those two locations have the same speed as each other. So that means that there's no difference in speed. And remember, with all of these deltas, we're not comparing, for instance, speed with the pump versus speed without the pump. We're comparing speed at one location to speed at the other location. And those two locations have the same fluid speed. So that means there's no delta V squared. However, the current in one pipe with the pump and the current in the pipe without the pump are going to be different currents. In fact, it tells us how different they are. They're different by a factor of 3. So we should actually fill in, I would recommend filling in subscripts here. Like with no pump, let's say this is I with no pump. I sub NP, no pump. Whereas with the pump, we're going to have, let's fill in current with pump. I'll just call that I sub pump. So let's just use I sub NP to mean current with no pump and I sub P to represent current with the pump. We can now set those boxed right sides of the equations equal to each other. The right side of the equation without the pump and the right side of the equation with the pump have to be equal to each other because the deltas on the left side of the equation are the same for both. So we can write this as negative I with no pump times resistance equals the energy density of the pump minus current with the pump times resistance. Any questions on that so far? The epsilon here represents energy density. So it is energy of the pump per unit of volume, but we often just write that as epsilon. So the epsilon here represents energy density of the pump. And these are all energy densities. We don't really care about the total energy of the system. All we care about is how concentrated the energy is. So all of these are energy densities. And what are we trying to solve for here? What's our only unknown left? Yeah, we should be able to isolate R here. And let's go ahead and fill in some values. For instance, we know the current with the pump is 12 cubic meters per second. And we know the energy density of the pump is 20,000 joules per cubic meter. And also, what do we know about the current without the pump? What's the one thing this tells us? Yeah, it changes by a factor of 3. Would you expect that to mean 3 times as much or 1/3 as much? That is, if you remove the pump, would you expect the current to get faster or slower? Yeah, so I would divide by 3 then. So that 12 changed, or 12 decreased by a factor of 3. That would be 12 divided by 3. So we get 4. So 4 cubic meters per second. And I think that should do it. We now have an equation where R is the only unknown left. So how would you isolate R here? Yeah, we could algebraically, since we've got the R, the variable we're trying to find on both sides, I would arrange to move all the instances of R to one side. So let's say we add 12R to both sides. 12 plus -4 is going to be 8 cubic meters per second times R equals 20,000 joules per cubic meter. And then what's our last step here? Yeah, divide by 8, 20,000 divided by 8 would be 10,000, 5,000, 2,500. And what would the units be there? If we're dividing by meters cubed per second, what units do we get on the other side of the equation? Not just joules per second, because remember, we're not multiplying by cubic meters per second, we're dividing by meters cubed per second. That's the same as multiplying by the reciprocal. So what do you get if you take joules over cubic meters and multiply by seconds over cubic meters? Yeah, the joules times seconds combines in the numerator. And what's the new denominator going to be? Yeah, meters to the 6th. So the units for fluid resistance are generally joules times seconds divided by meters to the 6th. And that's kind of just a jumble of units that doesn't really have much meaning on its own, but it's what's needed to make the units work out properly for everything else. So this would be the resistance of this section of pipe, 2,500 joule seconds per meter to the 6th. Any other questions on that one? And I think one really important takeaway from this, if you've got a situation where or a problem where it's describing some situation with fluid flow, and then it's describing how things become different when a change happens, I would recommend treating the system before the change happens and the system after the change happens as two separate fluid systems entirely. Write out a Bernoulli equation for the before situation and write out a Bernoulli equation for the after situation. Write out both of those equations and then compare the results algebraically. Maybe even solve for some variable and then compare the results, or set them equal to each other, or treat it as a system of equations. It does sometimes take time, but the more practice you get with it, the faster it becomes. So I would recommend getting as much practice as you can. Try out many problems, and look for similarities, look for patterns. Like as soon as you see a situation where something is changing, I would just recommend write out a Bernoulli equation before and a Bernoulli equation after, if you're making some change that changes the results. And then focus on what do you know is the same about these equations, what do you know is different about these equations. If there's an entire side of the equation that's the same on both, then set the other sides equal to each other. Or if not, maybe use substitution. Solve for one of the variables that shows up in both equations and then substitute it into the other equation. And then the rest is algebra. Any other questions on that one so far? Oh, how do we know to create an equation that illustrates no pump? It tells us what's going on with the pump, but it also tells us what happens when the pump is turned off. When you turn off the pump, what happens? So that means that since it's describing a situation with the pump, but it's also describing a situation without the pump. So that suggested that we want to also look at what's happening without a pump. So we draw out the exact same section of pipe, but with no pump, and see what happens there. And why did we divide by 3? Specifically tells us when we turn off the pump, the current changes by a factor of 3. Changing by a factor of 3 might mean being multiplied by 3 or might mean being divided by 3. So we're going to have to choose which one. Presumably, the absence of the pump would make the current flow slower than it did before. So I would choose dividing by 3. But if you're not sure, you could always try both, multiply by 3 and divide by 3 and see which one actually makes sense in the final result. I suspect if we had multiplied by 3 instead, we'd end up with a negative value for resistance, and that doesn't make any sense. Any other questions on that? And what else are we dealing with in the next part? The pipe breaks. and water flows out at this location. And we want to know, would the current increase or decrease or stay the same? And here we're talking about the with pump situation. So we'd use this equation. If the pipe breaks and the water flows out here instead of at B, what difference is that going to make in the equation? Well, for pressure, what do we know about pressure at point B in the first place? What's the one thing this tells us about point B? Specifically, what constant pressure? Yeah, point B, at point B, the pipe is open to the atmosphere. So we know that point B is atmospheric pressure. If we crack the pipe here, let's say we call this location C instead. So taking a look at location C, if we rewrite the equation from A to C instead of from A to B, the pressure difference hasn't changed because pressure B was at atmospheric pressure. Point C is now also at atmospheric pressure. So from A to C, the pressure change is the same as from A to B. The height difference hasn't changed because C and B are at the same height anyway. The pump hasn't changed because we still have the same pump there. But what do you know about resistance from A to B versus resistance from A to C? What would generally happen to resistance if you make the pipe shorter? Yeah, shorter pipe is going to be less resistance. In general, we should expect resistance to be directly proportional to length of the pipe. So all of the things being equal, a longer pipe will have more resistance and a shorter pipe will have less resistance. Because if the pipe is shorter, there are fewer opportunities to lose energy to dissipation with the walls. So if we break the pipe open at C, the fluid is now traveling a shorter distance through the pipe. It's experiencing less resistance overall. If everything else stays the same drop in pressure, same drop in height, same boost from the pump, but now a smaller, weaker resistance, what does that tell you about the current? Less resistance is going to mean what about the current? Yeah, I would expect an increased current, more current than there was before. Because if we've effectively decreased the resistance, we've made it, I mean, conceptually, we've made it easier to flow. If it's easier to flow, but everything else is the same, we should expect a faster flow rate. We can also look at this algebraically. If you solve for current, you're going to end up with a bunch of stuff divided by R. If you divide by a smaller R value, you're going to get a larger result. So you can look at this conceptually or algebraically. Both methods suggest that a smaller R means a faster current. Whereas in part 3, we're looking at the same situation with the pump and everything, but we've made we've replaced the pipe with a smaller cross-sectional area. The pump from C to B, yeah, we're effectively, since we're cracking the pipe open at location C, we're assuming that location C is open to the atmosphere and all the water can spill out through location C. So if all the water is spilling out through location C, then the rest of the pipe from C to B can be ignored. Realistically, maybe some of the water does continue flowing through there, but if location C, actually, I guess it wouldn't. If location C is open to the atmosphere, then C and B both have the same pressure and same height. So there's no reason for current to flow from C to B. Yeah, there's not a hole in the pump. There's a hole at location C, the dashed line shown here. The pump is still providing the same energy density boost that it did before. Yeah, there is a hole in the pipe. We're assuming that there's a hole in the pipe that makes location C have the same pressure as the atmosphere. And if there's no difference in pressure from C to B and also no difference in height, then there's no reason for fluid to flow. Because if you were to write out a Bernoulli equation from C to B, we'd have no pressure difference because we know they're both at atmospheric pressure, no height difference because it's a horizontal pipe, no cross-sectional area difference, so the entire left side of the Bernoulli equation is 0. There's also no pump, so current has to be 0 as well. That is, no current flowing from C to B. Yeah, I think that either way, we're really just saying that location C has been modified so that it's now at atmospheric pressure. It's now open to the atmosphere. So that's really the important thing here, that by opening up the pipe at location C, C is now open to the atmosphere. So location C now has atmospheric pressure. Any other questions on part 2 so far? And then in part 3, we're going back to the same pipe as part 1 with the pump, but we're replacing the pipe with a narrower pipe. We're keeping everything else the same, but we're making the pipe narrower. And what happens to the what happens if you make the pipe narrower? What effect would that have on the equation? So we're not breaking the pipe, we're still going from A to B. Velocity might be affected, but since we're comparing A and B still have the same cross-sectional area as each other, we should still assume there's no difference in the speed squared from A to B. Because we're still having a uniform cross-sectional area throughout the pipe. It's just a smaller cross-sectional area than it was before. And what would be different there? So what would be different in the equation? Have we changed the pressure difference from A to B? Have we changed those pressures? What do we know about the cross-sectional area at location A and the cross-sectional area at location B? Yeah, they're going to be the same. We are making the cross-sectional area smaller, but we're making it smaller, presumably by the same amount throughout the entire pipe. And for the kinetic energy density difference, it doesn't really matter what the cross-sectional area is. What matters is there a difference in cross-sectional area from location A to location B? So we've made the pipe smaller. So that might look something like, if we make the pipe smaller, or thinner, I guess I should say. So a narrower pipe. So we've made the whole pipe narrower. But all we need to care about in terms of should we include kinetic energy density or not is comparing the cross-sectional area at A and the cross-sectional area at B. And what are we assuming about those cross-sectional areas? Yeah, those are the same cross-sectional area as each other, right? It doesn't really matter what they are compared to what they were before the change. What matters is what they are compared to each other, those two locations right now. Because remember, in any Bernoulli equation, you're not comparing what's going on right now to what was going on earlier or what will be going on later. You're comparing what's going on at this location and this location right now at the same time. And since A and B right now have the same cross-sectional area as each other, that means there's no difference in kinetic energy density. Location A and location B have the same fluid speed. They've got a difference in pressure, same difference in pressure as they did before. They've got the same difference in height as they did before. There's still a pump between them. Has the resistance changed? According to this problem, the resistance has not changed. It says the total resistance of the pipe has not changed. So under those circumstances, with that assumption, we've got the exact same equation. Same pressure difference as before, same height difference as before, same pump as before, and same resistance as before. So yeah, in this case, that would mean current would be exactly the same as it was before, because nothing else in the equation has changed. However, this problem is extremely unrealistic. What would you expect to actually happen to resistance if you make the whole pipe narrower? Yeah, resistance is going to increase. So this is actually a very unrealistic problem. If you decrease the resistance, if you decrease the cross-sectional area of the pipe, if you make the pipe narrower, it's going to be more difficult for fluid to flow. So I would realistically expect a decrease in cross-sectional area to lead to an increase in resistance, which would make the current flow more slowly. The only way to really get around that is if you make the cross-sectional area smaller and also do something else to balance that out. Like decreasing the cross-sectional area will make the resistance larger. You could also make the resistance smaller again to balance it out by maybe substituting a different fluid, fluid with lower viscosity, for instance. So if you shrink the cross-sectional area, but also replace the fluid with something less viscous, you might be able to balance it out so that the resistance doesn't change. But realistically, if the only thing you're changing is shrinking the cross-sectional area of the pipe, that will increase resistance. Any other questions on this situation or this practice quiz? Or any other general questions about fluids and pressure and stuff? Then let me pull up that other practice quiz and we'll see if we can get a start on that as well. Can you see this one all right with the 3 standpipes? Okay. And we're trying to, given this setup with 3 locations with different area or narrow cross-sectional area, then wider, then back to the same narrow again. And we've got a pump. We want to rank the water levels in the 3 standpipes, figure out which one is higher or lower water levels. And what does the water level in a standpipe represent? Like if a standpipe has a higher or lower water level, what does that really tell you? That is what determines how high water is going to rise in a standpipe. Like if water rises up to a certain level, yeah, that tells you the gauge pressure in the pipe underneath. So when it says rank the water levels in the 3 standpipes, that really just means we want to rank the pressure in the flow pipe underneath. Figure out which location is at the highest or lowest pressure. So let's take a look at the changes. If you're comparing, what would be 2 locations that would be easiest to compare, do you think? If we're considering locations 1, 2, and 3. What, because Bernoulli equation is all about comparing a pair of locations. Yeah, let's try 2 and 3. That way we can at least ignore the pump. If we're comparing 2 and 3, what's the only thing changing from location 2 to location 3? Yeah, the area is changing. So we've got, at 2, we've got a wide area. At 3, we've got a narrow area. What's that really the indicator for? What does that tell you is also changing from 2 to 3? Yeah, we've got a change in kinetic energy density. Wide area, what does that tell you about the speed? Versus narrow area, what does that tell you about the speed? Right, wider area means a slower speed. A narrower area means a faster speed. So from 2 to 3, we've got an increase in kinetic energy density. And if the kinetic energy density is increasing, what else would you expect to be changing? Right, we're going to have a difference in pressure to balance that out. So from 2 to 3, we've got an increase in kinetic energy density, and therefore what change in pressure? Yeah, if the kinetic energy density is increasing, something else has to be decreasing to balance it out, especially since we're assuming there's definitely no pump from 2 to 3, and we're also assuming no resistance. So an increase in kinetic energy density has to be balanced by a decrease in some other kind of density. There's no change in potential energy density because 2 and 3 are at the same height. So we've got to have a decrease in pressure. That tells us that that location 2 is going to have a higher pressure, and 3 is going to have a low pressure compared to each other. Because from 2 to 3, we've got to have a decrease in pressure. So that suggests high pressure is going to mean the water rises up to a high level in the standpipe. Lower pressure means the water doesn't rise as high in the standpipe. Any questions on that so far? And what about location 1? We still need to figure out how location 1 compares to the others. So what other point do you want to compare location 1 to? Yeah, I think that's a good way to approach it. If we compare 1 and 3, 1 and 3 have the same cross-sectional area. So we at least wouldn't have to worry about any kinetic energy density. What's the only thing really going on from 1 to 3 that we do care about? Like if we were to write out the Bernoulli equation from 1 to 3. Yeah, well, it's not so much pump and no pump, because there's no pump at location 1 and no pump at location 3. A pump isn't really about being at the location. The important thing about a pump is that it's on the path from location to location. Like if we mark location 1 and location 3, neither one of those locations has a pump. But the important thing is the path from 1 to 3 passes through a pump. So that means the equation comparing 1 and 3 will include a pump because it's on that path. Whereas when we're comparing 2 and 3, that path does not have a pump on it. So that means for the 2 to 3 Bernoulli equation, we would not include the pump. But the important thing for pump and resistance is the path between those. So comparing 1 and 3, there certainly could be a pressure difference. That's what we're trying to find out. Is there any difference in height from 1 to 3? Right, no difference in height. So we can ignore the rho g delta y term. 1 and 3 are at the same height as each other. Any difference in speed squared from 1 to 3? What's really the actual indicator for kinetic energy density? Yeah, and there's no change in area from 1 to 3. There is a wider area in between, but if we're just comparing 0.1 and 0.3, we're just looking at the area at 0.1 and the area at 0.3. They're the same cross-sectional area, so that means no difference in speed. There is a pump between those, so we would include energy density of the pump. But we're also told resistance is negligible, so we can ignore the IR term. So it looks like all that's left is delta pressure equals energy density of the pump. And that's it. And as we go from 1 to 3, is the pump causing an increase or decrease in area? Or sorry, increase or decrease in pressure based on the direction the pump is pushing? Yeah, it should be causing an increase. Generally, a pump will have a directionality associated with it, an arrow showing which direction it's pushing. It's pushing in a direction that causes high pressure in the zone it's pushing on. So the pump is causing a low pressure zone on the left side and a higher pressure zone on the right side. So from 1 to 3, going through the pump in the correct direction, the pump is causing an increase in energy density. So E pump should be treated as a positive term, therefore delta pressure is positive. So 3 has higher pressure than 1. Relative to each other. And since we already said 3 was low pressure compared to 2, that means 1 is even lower pressure. So we can say location 1 is very low pressure. Which means it's going to rise in the standpipe even less than location 3 did. Or we might say 1 is low pressure, 3 is, let's say, medium pressure, and 2 is high pressure. Any questions on that ranking so far? Or any other questions on how to use standpipes like this? And in general, if you're comparing multiple locations, keep in mind Bernoulli equation is all about comparing 2 locations. So try pairing them off. Compare 2 and 3, 1 and 2, 1 and 3, whatever pairs are useful to try out until you're able to rank all of them in order. Part 2, we're looking at the same situation, but there's resistance now. So we can't assume no resistance anymore. And it looks like we now have information about speeds. We know speed in region 1, and we also know the cross-sectional areas. So speed in region 1, 3 meters per second. And we also know the area in region 1, which is the same as area in region 2. And if we know that information, how can we find the speed in region 2? What equation would relate these quantities together? Yeah, we can use the continuity idea that the current is the same. Current 1 equals current 2. And current, since it's fluid current, can be written as area times speed. So area 1 times speed 1 equals area 2 times speed 2. Speed 2 is the only unknown there, so we can just divide by A2. The ratio of areas is 2 to 1. So A1 over A2 would be 1 over 2, 1/2. So speed 2 is 1/2 of speed 1. In other words, 1.5 meters per second. So that's the speed at location 2, 1.5 meters per second or 3/2 meters per second. And then speed 3 goes back to the same as speed 1 because it's returning to the same cross-sectional area. So we now know the speeds everywhere. And it also tells us the water levels in each standpipe, or at least the differences in water levels. What does the standpipe tell you? If there's a difference in water level in the standpipe, what could you convert that to? Like if you know one of the standpipes is 0.2 meters higher than the other, what does the standpipe tell you about the fluid underneath? Yeah, that's all about pressure, specifically gauge pressure. But since what we really care about is the change in pressure, that's fine. So I would just convert each of these standpipe height differences to a pressure difference by doing what? How would you convert a height difference to a pressure difference? For instance, 0.2 meters of water. How would you convert a difference of 0.2 meters of water into an actual pressure difference in pascals? What formula would relate a height difference to a pressure difference or convert it to an energy density? What's the one formula you have that relates height and pressure or height and energy density? Yeah, we can figure out using the potential energy density formula, rho g delta y, density of water times gravity times the difference in height of the standpipes will tell you the difference in pressure at the bottom. So we know from 1 to 2, there's a standpipe difference of 0.2 meters. If we multiply density times gravity times height, or times difference in height, that should tell us the difference in pressure. So if we take density for water, 1,000 kilograms per cubic meter, times gravity, round that off to about 10 meters per second squared, times the difference in height, 0.2 meters, that'll be the difference in pressure. So 1,000 times 2 would be 2,000. So 2,000 pascals. That tells us, based on the standpipes, that the difference between pressure 1 and pressure 2 is a difference of 2,000 pascals. And then you could do the same thing from 2 to 3. We should end up with 6,000. So the difference in pressure from 2 to 3 is a difference of 6,000 pascals. With those pressure differences, I think it should be possible to set up those Bernoulli equations. So again, Bernoulli equations, let's say from 1 to 2, from 2 to 3, maybe also from 1 to 3. Write out what terms are changing, fill in all the values you know, and based on the standpipe description, we now know the difference in pressure from 1 to 2 and from 2 to 3 as well. So fill that in. And it looks like we've got two unknowns here. We don't know the energy density of the pump, and we don't know the resistance of the pipe. But if you can set up two equations, then that's enough to solve for two unknowns. So try setting up two Bernoulli equations comparing these points. Treat that as a system of equations and solve for the two unknowns. Any other questions on that? All right, then I will see you next time. You're welcome.